For the rest of the session, chairman is going to be Ferran Macià, who is professor of the University of Barcelona. Ferran has been, he was doing his PhD in Barcelona and then working also in several places. He has had stays in China, in Cornell, but he was a postdoc at New York University during some time working with Andy Kent. So he went back to Spain to work at the Institute of Material Science of Barcelona, the Spanish Research Council, and then recently, some couple of years ago or so, he is teaching at the University of Barcelona. So Ferran, thank you. I want to thank you again for your nice lecture on Wednesday, and the floor is yours to chair the session. Thank you very much.
Okay, thank you very much, Fernando. I'm glad to chair this session and having a pleasure to just introduce Professor Andy Kent, which is probably one of the persons I learned more physics in my career. So Andy is professor of physics and actually is a director of the Center for Quantum Phenomena at the New York University. And well, he received a PhD from Stanford, and he conducted postdoctoral research in Geneva and at IBM in New York. And then he became assistant and associate and finally full professor since 2004 in New York University. So today, I mean, he'll be talking about spin transfer torque and spin orbit torque oscillators. And I think we all have heard quite a lot about spin torque and dynamics of magnetization, but I think it's a good opportunity to hear from him such particular applications such as the oscillators. So, okay, I'll leave you with Andy Kent, and I hope you can enjoy the lecture.
Can you see my screen there?
Perfectly, Andy.
Yes, thank you, Ferran. As you know, I have very fond memories of you being in New York, and I can say the same. I learned a lot of physics while you were here. So, and I'm really happy we could continue this collaboration for many years on spin oscillators and even exchanging students. So, and I want to thank Fernando for inviting me and for including me in this group and the other organizers. It's really a pleasure to be here. And to be able to tell you a little bit about spin transfer and spin orbit torque oscillators. So the outline of my talk is that I will tell you a little bit about the basic physics of spin transfer torques. I'll go through the discovery of spin transfer and spin orbit torques, talk about spin dynamics and spin waves, and some of the materials and geometries that are used to make oscillators. And I'll give kind of a tour of the different kinds of oscillators that have been created and studied. Spin Hall, magnetic vortex oscillators, easy plane oscillators, and then one of the topics that we've been working on a lot experimentally, nanocontact spin oscillators and magnetic droplets. I'll talk about coupling of magnetic oscillators, which is still, I'd say, a forefront topic in this area, and also talk about current research topics. So I'll start by saying, you know, that I know you've heard a lot in this school, so you're going to hear again probably things that you've heard. But as a famous physicist once said, never underestimate the joy that people derive from hearing something they already know. So you should hear something you already know now in the next few slides. One is that the important start of Spintronics was the discovery of giant magnetoresistance, and where the resistance change is associated with the spin of the electron. So these were discovered in magnetic multilayers, magnetic, non-magnetic, iron chromium layers, in which the layers would be antiferromagnetic at zero field, but then you could apply a field and align them in a parallel way and see a resistance drop of about a factor of 2 at low temperature. Or if you just had 2 layers, you could see a resistance change of several percent at room temperature at an abrupt change. So this you now know is associated with the fact that ferromagnetic elements have spin polarized electrons, and their conductivity depends on their spin direction. And this got the label Spintronics, which is short for spin transport electronics, which in one definition is the control of current using the spin of electrons. Another extremely important development was the optimization, you could say, of what are called magnetic tunnel junctions. So magnetic tunnel junctions, instead of metallic layers, are two ferromagnetic layers separated by an insulating barrier. These were actually studied in the 70s but very, very tiny effects were observed. That is just a few percent change. And the technology wasn't good enough to allow you to make a barrier that was both uniform and could maintain a spin polarization. And now we know how to do this. So you have the same kinds of effects. When the layers are aligned parallel, you can have a different conductance between the electrodes than if they're anti-parallel. And you can understand this as a property of the densities of states of the ferromagnetic layers. That is, that there's a different density of spin up and spin down electrons, majority and minority spins. And when the layers are aligned, you have spin, and the tunneling conserves spin. You have tunneling from a large density of state to a large density of state, which gives you a low conductance. And when the layers are anti-aligned, you have a tunneling from a large initial density states to a smaller state. So you have a lower conductance. And actually everything can be understood, at least in the first model, just in terms of the polarization of electrons at the Fermi level, this being the density of states of the electrodes, left and I would be left or right. And the magnetoresistance would be directly related to the polarization. Now, the polarization of most ferromagnetic materials is about 0.4. So you could expect a TMR, again, of about 20, 30, 40%, depending exactly on how these are arranged. But what you can now see is that in modern samples, that is materials which have MgO, a crystalline barrier, you can get changes of resistance of a factor of 3. So there's been really a perfection of the ability to make these barriers. And if the barriers are crystalline, you have additional selection rules in the tunneling process that can give you even higher magnetoresistance than you expect based on this simple model of tunneling. So really interesting was that this was predicted before it was observed, or about the same time, depending on who you ask. In iron MgO iron sandwiches, it was predicted that you could have 1,000% change in resistance. I think the largest change so far is about 600%. So there's large changes in resistance, and this is an important thing to know, that the tunnel junction is a central element to most spintronic devices. I think the other thing we have to consider is the idea that not only does magnetization control current, but current can control magnetization. So putting a current on one of these multi-layers or tunnel junctions in the right way can cause the magnetizations of the layers to change. And this was predicted, again, theoretically, before it was seen experimentally by John Sonzuski and Luc Bourget. And they won the 2013 Oliver Buckley Prize. That's a prize of the American Physical Society. Actually, it's the highest prize in condensed matter physics, and for predicting spin transfer torque and opening the field of current-induced control over magnetic nanostructures. And these are the foundational papers. These are the ones that I think, if you're interested in the form, in how this field started, the spin transfer, this 1989 paper is a really nice paper, can be understood with basic quantum mechanics. I'll just tell you a little bit about that. So the basic quantum mechanics, this is the paper, conductance and exchange coupling of two ferromagnetic magnets separated by a tunnel barrier. And what's considered this paper is two ferromagnetic layers, so two electron gases that are separated by vacuum. And you model the ferromagnet as having as an electron gas, a metal, in which the field is very, very large, local field. So this is not an external field, but an exchange field. And that leads to a spin polarization of electrons at the Fermi level. And then what was considered is, what if the two fields in those ferromagnets are different? So what if the magnetizations are not oriented along the same axis? And one thing John Slonczewski found was the Julier valve effect. That's what I just told you, that the magnetoresistance is related to the spin polarizations of the electrons. The other effect he found is that these two layers are exchange coupled. That is, they're not independent. If electrons can tunnel, that means there's wave function overlap. And if there's wave function overlap, that means there are exchange interactions between the layers. So there's exchange coupling between the layers. And the third effect is the new effect. It's a new irreversible exchange term in the coupled dynamics of the ferromagnet. And he writes, for one sign of the external voltage, this describes relaxation of the Landau-Lipschitz type, which you've probably heard about in the earlier lectures. And for the opposite sign, it describes a pumping action, which can cause spontaneous growth of magnetic oscillations. And that's the spin transfer torque, essentially. It's a irreversible interaction. It doesn't conserve energy, and it leads to a pumping action. That is where the magnetization can start to precess. And that's the basis also of oscillators. His idea basically was, if you have the two layers at some different angles, these can represent the angular momentum of the two layers, you get a spin current. If they're the same, you get a spin current that's the average, the geometric average of those two, and you will get torques that cause these to rotate in a windmill-like fashion. So these are the spin torques, and what's really interesting is you might think you're exchanging angular momentum. These two should rotate in opposite directions. In fact, they rotate in the same direction. So an interesting homework problem is to ask, where does the angular momentum come from, since it's not directly exchanged between these two ferromagnetic layers. So, and the other thing he writes here is that this relation connecting these three effects suggests experiments involving small spatial dimensions. And we'll see that's very important for physics reasons and also for practical reasons, that the samples have to be small. You could say the real reason is that you need relatively large current densities to have substantial effects. You have electrons that are transported, a small group of electrons that are transported at the Fermi level, and they affect the entire magnetization, so all the other electrons. So that's a remarkable thing, that just a small fraction of the Fermi C can affect all of the electrons, and you need relatively high current densities for that to happen. And the applications are in magnetic random access memory. I won't talk too much about that, but the idea that you can switch the direction of magnetization using currents that pass just through the elements is an important thing, because it means you can act locally on the magnetization. This is an interaction that occurs just where the current flows, even though it can generate fields that are outside that region. The fields are not the critical part for this interaction. It's really the flow of spin angular momentum. Okay, so let's say I've told you a little bit how spin torques work. You pass a current through ferromagnetic layers, and that generates a polarization. And typically what you do is you have one layer that's thicker or pinned in some way, so that it doesn't respond to the torques. It will experience a torque, but if it has a much larger angular momentum, it won't respond as dramatically. And you have a second layer that responds, that can oscillate or switch. Here, the currents are, the charge current and the spin current are more or less proportional to one another. We call this the polarization. And Sergey discussed this as well. The flow is now, these flow through the same cross section. And the other way you can generate spin currents is using spin orbit torques. That was the subject of the last lecture. You can pass a current laterally and generate a spin current that is vertical. So this is characterized by the spin Hall angle. And here the charge current and the spin currents are not in the same direction. The spin current is transverse to the charge current. Okay, these are written in some way that where that these quantities are dimensionless. So the spin, to get to a spin current, you have to, this is actually a spin current written in terms of a charge current. So to convert it back into a flow of angular momentum, you need to multiply by h bar over 2e. And so here you see that you have a spin current that's directly related to the charge current. And here you have a spin current that can be larger than the charge current by a geometrical factor, because the currents flow through a different cross section. So this is very interesting. I mean, it's interesting for a number of reasons. One is the charge current doesn't directly flow through the magnetic element. So this could be a magnetic insulator. You could still exert torques on that layer. And secondly, you get this amplification effect where this dimension could be about 10. That is, the layer could be just a few nanometers thick, and this magnet could be tens of nanometers thick. So you have a number of interesting aspects. And the materials here, there's a wide variety of materials that now show these kinds of effect. The initial experiments were done on platinum, tungsten, and tantalum, and these showed large spin Hall angles. And there are two very nice papers on this that sort of launched the field. This was launched by a discovery of these large torques. And since a question was asked last time about spin orbit coupling in ferromagnetic materials, I'll mention a paper that we published last year, Jonathan Sun, Chris Safansky, and Junwen Xu and I, that shows that you can get spin currents from, if this layer is a ferromagnetic layer, which have a symmetry given by the planar Hall effect. And why is that important? Well, one thing is here, the spin current is a tensor. It has a flow direction, in this case z, and a polarization direction, in this case set by the reference layer. Here, in this case, the flow direction is also in z, but the polarization is set by geometry. So the spin current tends to align perpendicular to the current flow direction and in the plane of the interface. So that sets, that's not always the case. That is, crystalline symmetries can cause different directions of the polarization. If you, in this planar Hall-driven spin torque, these directions are set by the magnetization, just like here. So you have a way to generate spin currents with a direction set by the direction of magnetization. That's a side note, but the key thing is to remember that spin currents have directions and polarizations. They flow in certain directions and they have a certain degree of spin polarization. Okay, so if you want a simple picture of how spin transfer works, it's a conservation of angular momentum. You imagine an electron passing through a magnetic layer. If the electron spin direction is changed, there's a change in angular momentum. And to conserve angular momentum, that angular momentum has to go somewhere. It can go into the ferromagnetic layer, that gives you a spin torque, and it can also go into other degrees of freedom, into lattice degrees of freedom. So the best case is that the entire angular momentum goes into changing the magnetization of the ferromagnetic layer, and that leads to a torque then that's related to the change in the direction of the spin, the polarization of the spin, and the number of electrons per unit time crossing that interface times h bar over 2, the angular momentum each electron can transfer. Basically, most angular momentum you can get is the transverse component of the electron spin. So that's the concept. That gives you this relation, you set up this spin polarization with a second ferromagnetic layer, or with spin orbit torques, and that sets the polarization. And you can read out the state through resistance changes. So the simplest way to detect spin torques, is if you see a change in resistance when you pass a current, because if the layers magnetizations change, that leads to a change in resistance by the TMR effect or the GMR effect or AMR effects or other transport effects. And you'll see probably the next talk that there are also very nice ways of directly seeing how the magnetization is affected by currents and other forces. If you like to look at pictures, which I do, here's a kind of picture of how this works. The electrons move and they reorient, and in reorienting, they exert a torque, and that is all electrical change in magnetization. Okay, so this is, I think, also a reminder of what you've seen earlier in the talks. That is, that you can model the spin torques by adding another term to the LLG equations, the so-called Slanzewski term or spin torque term. And this term has the form of a triple cross product where MP is the polarization of the electrons. This factor is proportional to the current. It also has some material parameters and fundamental constants. And you can write this term in the following way to show that it's the transverse component of spin that is leading to a torque, the component that's not aligned with the magnetization of the layer. So we can basically, this is a nonlinear equation, and can have all kinds of interesting solutions. The simplest case would be if the polarization and the effective field are aligned. Then the spin torque term is collinear with the damping term. And when the spin torque term has the right sign, the pumping action that John Slanzewski talked about, it can equal the damping or even be larger than the damping. And that's the condition for getting a oscillator or switching. If it equals the damping, you could have a precessional motion of the magnetization around the effective field. And if it's the opposite sign, it will tend to damp the magnetization and move it faster to its equilibrium position along the effective field direction. The time scale of the oscillations is set by this term, the precessional term. It's 28 gigahertz per Tesla. So if you have a effective field of a Tesla, you expect precessions frequencies of 28 gigahertz. And because of damping, there's a threshold. The spin torque has to exceed some threshold set by the damping in order for this dynamics to occur. So there's also possibilities of having a spin torque that leads to a field-like torque. That is a term that's proportional to the current but multiplies M cross MP. And this is called the non-adiabatic S torque. It can be included in a field so that it would be somehow changing the frequency of the motion. And it can be important, but the term that causes the instability is this spin torque term, because that's the dissipative term, the term that can't be written as a gradient of a potential. So again, to summarize, the fast dynamics is associated with this gyroscopic term. Damping and the spin torque are smaller by about a factor of 100. And if these two are collinear, you can show that this term here can act as an anti-damping torque for one sign of the voltage or the current. And the adiabatic torque, this term is zero when these two are strictly collinear. So you really need it's the transverse component of the spin polarization. You need an angle in order to get things going. Sometimes that can just be a fluctuation, a thermal fluctuation. Sometimes you can engineer that into your sample in order to have an angle and to get the torques going, to get the magnetization out of equilibrium. Okay, so this is a figure that my colleague and collaborator Jonathan Sun gave me to show the kinds of dynamics you get if you have a uniaxial magnet. If your current is smaller than some threshold and the magnetization is perturbed, this is a so-called macrospin model, just considering the ferromagnet as having one giant spin. So it would apply to a single spin or a very small magnet. You can see the magnetization will spiral and damp and eventually be along the easy axis. If the current is very close but just above the threshold, the magnetization oscillations will increase in amplitude and keep going until they reach the equator, and then the magnetization will damp into the opposite pole. So you can go from the north to south pole. And if the current is much larger than the threshold current, this can occur in fewer oscillations. And the threshold current for a uniaxial magnet is again related to the material parameters, the magnetization, the anisotropy, the volume of the magnet, the damping and the spin polarization, as well as fundamental constants. For a uniaxial magnet, there's a simple way to write this, that it's proportional to the energy barrier in a macrospin model between the up and down states times the damping divided by the polarization and fundamental constants. So this gives you the scale. If you want a magnet that's stable at room temperature, where the barrier U is 60 times K times room temperature, 300 K, you find the threshold current is 15 microamps. So that's a reasonable current. It doesn't require that large a current to get to this kind of interesting dynamics. So we're mostly going to talk about spin waves and spin wave excitations rather than switching. And one geometry in which you can create spin waves is if you have a nanocontact. If you confine the current to a small region and pass a current through that layer, it can't switch usually because the background is fixed or there's no forces on the background. And instead you can get waves that propagate away, and you have an oscillator that's generating waves where the generation source is the spin torque that's acting in the region where the spin polarized current flows. I hope that's clear so far. If I could look out and see, I would maybe see some people who are confused and some people who aren't, but let's keep going. So let me talk a little bit about geometries and materials before I talk about some examples of spin oscillators. So as I mentioned, the key thing is you need relatively large current densities, and this is for practical reasons that you don't want to burn up your sample. You have to have a small structure. So and the other reason, the physics reason, is you want the spin transfer torque to dominate over any Oersted fields associated with the charge current. So if you have a large structure to achieve large current densities, you need large currents, which generate large fields. And those large fields can be the things that actually cause the dynamics. So by making, that means you can find typically below about 100 nanometers, maybe 200 nanometers. And there are a number of geometries that do this. One is you can have this kind of bilayer or trilayer, 3 layers, 2 magnetic layers separated by a non-magnetic layer, and make a nanocontact. In fact, some of the first experiments were done by using an STM-like setup where you just put a tip into a multi-layer. These you can measure the IV characteristics, and you'll see the current-induced excitations by a little blip. That is, as soon as you excite the magnetization by GMR, you'll have a little bit of an increase in resistance. You can make a pillar where you confine the layers, same 3 layers. This could be a tunnel junction or a metallic system. If it's metallic, it's called a spin valve. If this is an insulator, this is called a tunnel junction. And here you can see switching. So you'll see an IV curve that has usually some kind of background due to heating or other mechanisms, and then a jump in the resistance, which indicates switching from, say, parallel to anti-parallel. And then when you come back in reverse, you get the opposite. These kind of effects can be seen in single magnetic layers. You actually all you really need is an imbalance in the spin accumulation on either side of the layer. So you just have to break the symmetry in some way. We actually did experiments on this early on and showed you can get current-induced excitations in just one magnetic layer pillar. And as I mentioned now, the spin orbit torques allow you to generate these spin currents and excitations by having current flow underneath a magnetic element and the spin current flow through the magnetic element. And this has led to a new type of geometry where you pass a current through a nanoconstriction with a heavy metal that generates spin orbit torques, and that can lead to spin excitations in that region. So this is a very nice structure because it's relatively simple. You can take a thin film structure that just has 2 layers, a magnetic and a non-magnetic, the non-magnetic layer generating your spin orbit torques, pattern it, and create an oscillator. The key thing for an oscillator is that in some region of the material, the damping can be compensated by injecting spin currents. So that's the key feature. The new physics comes from the spin torque term proposed by Slonczewski that can lead to this compensation. Basically, can create a part of the material which has no damping or, in fact, negative damping, if you like. Okay, so I'm gonna now maybe in the next 15, 20 minutes, I'll give you kind of a tour of the world of oscillators. There are many, many types, and I'm sure to miss some, but I'll talk about maybe the kinds that are being studied most prevalently today. One is the so-called magnetic vortex oscillator. This is a oscillator built again with two magnetic layers, but with one of the magnetic layers in a vortex state. So this is a layer that where the ground state could be a vortex. That is, if the material is a soft magnetic material, doesn't have a large anisotropy, and you make it thick enough, the ground state can minimize dipole energies at the cost of exchange, and you can get a magnetic vortex. And if the polarizing layer is now uniformly magnetized, you can start to make that vortex move. And if the vortex center moves, actually it's confined to the disk, so really you distort the vortex, you can convince yourself that there'll be changes in the net angle between the magnetization of the reference layer and the free layer that would give you an oscillating voltage. And these generate very, very nice oscillators. They're typically oscillators in the gigahertz range, maybe 100 megahertz to several gigahertz. They're lower frequency than an oscillator that would oscillate because of internal effective fields in the Tesla range. But they're very high quality oscillators. And the first such oscillator I'm aware of was made by the Cornell group and published in 2007. And these had a quality, and I don't know what the record is now, but the qualities factors can be tens of thousands. And because this can be made of a tunnel junction, the signals can be very large, so you can resolve this easily with an oscilloscope, the response. So these are very, very nice oscillators that use a fairly big magnetic volume. The whole volume of the vortex oscillates in response to the spin currents. As I mentioned, another type of oscillator is the nanoconstriction type oscillator that's based on the spin orbit torques. And this kind of oscillator has oscillation frequencies that are larger typically because it's the internal fields that set the oscillation frequency. And the oscillating volume is also smaller. It's set by the size of the constriction. This was first done by Demidov and published in 2014. And they showed you can get oscillation quality factors of 1,000 and oscillation frequencies again in the 5 gigahertz and larger. In general, the line width is related to several factors, but one of them is the amount of energy in the oscillator. So that depends on the volume of the oscillator and other factors in the oscillation. So this is maybe very commonly studied because there are many different ways you can configure these oscillators, and the material set available is quite large. I'd say any combination of ferromagnetic and heavy metals or other spin orbit coupled materials can lead to these kinds of oscillators. I'll mention another type of setup where you can generate oscillations. That's where your free layer is essentially an easy plane magnet, and you inject a perpendicularly polarized spin current into that magnet. Then you can have oscillations in which the magnet actually oscillates around its demag field or mainly in the easy plane, and you can get very, very fast oscillations in this case. Oscillation frequencies could in principle be up to 10, 20 gigahertz. We've done recently an experiment on this. It's not really an oscillator experiment, but it does show that oscillations, you can put pulses in and record the final state of the free layer, whether it's parallel or anti-parallel to the reference layer. And you can see oscillations here that occur with a period of about 0.2 nanoseconds in this case. So that's another type. So I guess one of our favorite types of oscillators has been the nanocontact oscillator, and I'll tell you a little bit about some of its unusual dynamics. It turns out in this type of oscillator, you can generate solitons. So instead of just generating spin waves, you can form a structure like a vortex in some ways, but not topological, at least in its basic form. And it was actually a structure that was predicted in thin films with perpendicular anisotropy in the absence of dissipation. And this was predicted in the 1970s as a, you could say, as a theoretical construct, because no materials without dissipation existed. But it was realized by Mark Hoffer, Tom Silver, and Mark Keller that now with spin torques, you could create a region which had no dissipation. And when you have that, you can start to collect spin waves in that region. At least that's one way to think of it. And that region can act, its magnetization can reverse. So this is a perpendicular material. The red region indicates a part of the region that's reversed, and this is the MZ. So you can, as you increase the current, more and more of the magnetization reverses, and the spins are precessing in this region. At least at the boundary, there's large angle precession of the magnetization. And what's cool is that this oscillator has oscillation frequencies much lower than the spin wave frequencies in the material. So it's a mode which has a frequency lower than the ferromagnetic resonance mode, this indicated here by 1. And in some ways that makes it isolated from the spin waves modes. In other words, it doesn't couple strongly to modes that propagate away from this contact. So these are experiments that Ferran did while he was at NYU. We made nanocontact oscillators, which had a permalloy free layer and a cobalt nickel, permalloy fixed layer and a cobalt nickel free layer. Cobalt nickel can have an out of plane magnetization, and we pass current through these layers. So we created a dielectric here, put a hole in the dielectric and made a contact. This is what the way the sample actually looked. This was the 3 layers. This is the cobalt nickel copper permalloy, and then we opened a hole in this dielectric by reactive ion etching and deposited a cross layer of copper and to create a contact. And what we could see in this situation was that at low currents, there was an oscillation. This is measured with a spectrum analyzer, close to the ferromagnetic resonance frequency. And then at some current, you see a dramatic drop in the frequency. And this is consistent with the formation of this localized mode. You also see a step in resistance, which is what you'd expect from the GMR effect. That is, the layers, there is a field applied. So this layer has some angle, and now the region in the free layer is more anti-parallel. So this was first seen by Johann Ackermann's group, this electrical measurements. And we saw that these contacts this droplet can be metastable or stable at low temperature. So you can have a large region of metastability. And what we saw is a transition from a situation where spin waves are radiated away from the contact to a case where you get a localized mode. And we recently wrote a review article on this, which describes the physics and what the experimental situation is. So you can think of it as a transition from some kind of state with spin waves to a state with these droplets. And I think one of the exciting things was we were able to see this with X-rays by using X-ray microscopy, which you'll hear about in the next talk. So we were able to put these oscillators on membranes and then excite them with a current and see that once we got to a critical current, there was a large change in the magnetization in the contact region. And with Stefano Bonnetti and Hendrik Oldag and others, we were able to also show that you can take time-resolved movies of spin waves and watch them propagate. This was for an in-plane magnetized layer. So as I said, this is the whirlwind tour. This was the direct evidence that you're forming a droplet. The electrical data can only give you something indirect that you have to assume based on models of the physics of what's going on. So we've been thinking a lot about this, and have done a lot of work on this since, and we've been wondering, can you form, we have these vortex oscillators. There's a big emphasis now in research on skyrmions. The droplet is a non-topological object. Can you make it topological? And now Statuto has been working on this, on modeling this, and the answer is yes, under certain situations, you could expect to have a topological droplet form in a nanocontact. And there's some experimental signatures. I can say this has not yet been seen in experiment, but it would be very exciting because you could imagine then being able to nucleate skyrmions and in these kind of nanocontacts under the right conditions. Okay, so I think I have maybe 5-10 minutes left. Ron, right? Yeah, I guess I'll assume I have 5 or 10 minutes left.
You have it, Andy. You have it.
Okay, good. Thanks. So yeah, thanks. So maybe I'll say something more about coupled oscillators. I think this is a very interesting topic. So why would you want to couple oscillators? Well, it would be interesting, of course, if you could couple them. You could exchange information between the oscillators. There's also the hope that you could make a much higher quality factor oscillators, that you could have a coherent oscillation among many oscillators, which would reduce the line width of the oscillators. And I'll tell you a little bit more about that, that there are other applications you could imagine. So the first experiments were actually 2 nanocontact oscillators separated by some distance. And there were experiments done at NIST and in another group. 2 groups basically at the same time did a very similar experiment where you could separately contact these 2 oscillators and show under certain conditions you got an increase in power and a narrowing of the line width. So you went from having 2 separate oscillations to one oscillation where there's evidence of that the phase of the 2 oscillators was locked together. And here they could show also that the coupling mechanism is spin waves. So they could take the oscillator in another experiment and cut the free layer. And when they cut the free layer, the coupling went away. You can imagine that the oscillators are coupled by dipolar interactions and even by the fact that they might share the same substrate. So there's electrical connections between the oscillators. There's also these nano constriction oscillators. And as I mentioned, you can make these in a row, and then you can show that these couple in a kind of way where one oscillator couples to the next one along a chain. So it's a non-reciprocal coupling, at least the way I understand it. And here this was some years ago, was shown that in Johan Ackermann's group, it was shown that you could couple 9 oscillators this way. And I believe that there several times more now have been coupled in this way. And the evidence, again, as you can see, independent oscillation frequencies, and at some current, those merge, and you find just one oscillation of higher amplitude. And I'd say at the beginning of the field, it was shown by Bill Rippard at NIST that you can injection lock an oscillator. So you can lock an oscillator to an external source. If the external current is oscillating at some frequency, there'll be a range in which the oscillator locks to that external drive. So it's it's an oscillator where you have a oscillating drive and a condition for locking where the line width then becomes very narrow, reflecting the source, and a range over which in field and current in which you have this locked state, as well as enhancements of the output voltage and power. So those are the kinds of things you could do. I mean, the other things that one can imagine is now if you have them phase locked and you can control the phase difference, you can make antennas that would propagate spin waves in particular directions. So in the simplest case for a spin torque nano oscillator that's in a perpendicular material and you passing a current through the nano contact, you will generate waves that propagate out. If you have 2 nano contacts and they're phase locked, you can get a pattern of waves that go, and so you can direct spin wave energy in a particular way. If you have 3, you can generate a more complex pattern. And in general, you can use these as antennas to generate spin waves that would propagate in the way you want. And this is work we published in 2014. I think that this still hasn't been done, but I think in principle, there's no reason you couldn't generate spin waves this way and be able to control their output signal. And so you can imagine this could be important if spin waves are information carriers and you want to direct them in particular ways. So I'm coming now to say what are some of the current things people are working on. Say one is that we have these oscillators. We might want them to function as some kind of neuron, and I know you're going to hear from Julie Grolier later in this session. She's going to tell you all the beautiful things she's done with oscillators. You might want an oscillator that spikes, just like a neuron, and so you know you can take a nanocontact oscillator and might get spike. We showed a way you can do this using memristors. There's also the ways to do this with spin Hall nano oscillators. And there's ideas for doing it with antiferromagnetic oscillators. So that's, I think, the forefront of where people are working. We've seen that you make these oscillators now, they basically you can make good quality oscillators in the gigahertz range. Certainly the vortex oscillators, as an individual oscillator, have the highest quality factor. It would certainly be interesting to be able to increase the range of frequency. Could you make an oscillator that oscillated in the hundreds of gigahertz or terahertz range? Could you make it more tunable to current and field? That would be interesting. As was discussed earlier, the key thing that determines the energy required to generate these oscillations is the efficiency of charge to spin conversion. So increasing that can reduce the energy, as well as lowering the dissipation in the magnetic materials. Mostly now we're working with magnetic metals, and those almost always have damping greater than 10 to the minus 3. So that sets a threshold and determines the energy. And you'd like to be able to exert spin orbit torques on materials with perpendicular magnetic anisotropy. These generate the spin waves that can be radially symmetric from the contact, at least before you form a droplet. And spin orbit torques at this point are not very effective at exciting those types of layers. So there's a demand actually to find ways to do that with spin orbit torques that can excite perpendicular layers. Yeah, I think you'll hear about this in your next session. I guess that will be on May 28th. That these oscillators can be used to realize reservoir computing. And the key part is that they're nonlinear. They have some memory. They have a memory of relaxation time, and they can be designed to be not chaotic. So they can have a sequence of inputs and go somewhere reliably into some state in phase space. And this has been demonstrated for spin torque oscillators, actually vortex oscillators. Have been used to implement a reservoir computing. And the thought is that these oscillators can serve as the neurons, and they can also serve as the synapses. So the neuron can take a DC signal and convert it into a oscillating signal. And then you can use something called the spin torque ferromagnetic resonance to convert the oscillating signal back into a DC signal. And again, this is being pioneered by the group of Julie Grolier in Thales. Okay, so that was my rapid tour of spin oscillators. I hope I've given you some sense of the basic physics of spin transfer and the history of the discovery of spin transfer and spin orbit torques, and told you a bit about some of the current things that are being studied in experiments: spin Hall oscillators, magnetic vortex oscillators, easy plane oscillators, and one of our favorite, these nanocontact oscillators, as well as current research topics. And I might say at the end, I owe a great debt of gratitude to all the people I've worked with over the years on these projects. Some of the people who've worked on oscillators at NYU are highlighted in bold here. And we've had a long-standing collaboration with Hendrik Oldag at the Advanced Light Source to directly image spin excitations. And of course, with Ferran and Naul Statuto, my colleague Dan Stein, who's helped on the theory, along with Gabriel Chavez. I've worked with these easy plane oscillators with the group of BBN, and many others have contributed to my understanding of this physics. And this was the group here, my group in 2020. If you imagine January, this was almost our last time together as a group, just celebrating the Christmas holidays. We're hoping that January 2022 will have the same kind of picture, and this with everyone together again, and spending time in face to face and meeting face to face, and maybe having some of these schools face to face. So thank you very much for listening.
Thank you very much, Andy, for the nice talk. So I have a few questions so far, so I'm going to read them.
Okay.
So first of all, Juan de la Figuera is asking, and I think he's asking the right person, what is the status of antiferromagnetic based oscillators?
That's a great question. Great question. The status of antiferromagnetic oscillators is there's a lot of theory done, and people think that there's some beautiful experiments showing the inverse effect. That is, that if you excite an antiferromagnet with a terahertz field, you generate a spin current. And there's beautiful work in the group of Enrique Del Barco, who I think you know, and he's shown it so that in principle, the inverse effect should be possible, but it's not yet been seen. And so I think the physics says it should be there, but so far, maybe we haven't found the right materials or structures to see that. I think the challenges are, again, the current densities required, potentially. These are terahertz oscillators, so the threshold current is proportional to the frequency and the damping. So you can imagine you raise the threshold by, if you raise the frequency terahertz, you're talking about factors of several orders of magnitude. The damping of antiferromagnets can be smaller. So, but you still have to worry that maybe we haven't gotten to the right materials for seeing that. On the other hand, it may be that my feeling is this is something that will happen in the next several years as we understand better the materials aspects of this. But so I don't think there's a physics reason. But it is I think it's a challenging materials problem.
Okay, excellent. a few more. Okay. David is thanking you for the wonderful talk, and the question is like, with regard to the vortex core oscillators, can higher order geotropic modes be easily excited in a similar way?
I imagine this is a great question for Jovan Kim. I think he may have talked about that. I think the answer is yes. And I think he may have left. I don't see him there, but yeah, he was here in the earlier. He's in the earlier session actually. So I'll just give the simple answer, yes.
Okay, so next, Pradeep is having two questions, so I'll go one by one. So the first, he's thanking you also for the interesting talk. And the question, he says, I understood that the oscillators somehow could be mutually coupled by the dipolar coupling. The plot also depicts that the oscillators, again, get decoupled with increasing current to high value. What is the reason for that?
Oh, that's a great question. I think the reason is probably very specific to those particular oscillators. Each oscillator has what we call its own personality. That is its own agility, you could say, its own change of frequency with current. And I think that's the essential reason. That is, it's ultimately whether they couple or not depends on coupling and the difference in frequency of the natural frequencies of the oscillators. So if the frequency difference becomes too large, the coupling strength is no longer sufficient to keep them phase and frequency locked. I think that's the basic explanation. Then to get, I mean, Charlie, for every case, you might need a more specific, detailed understanding to know exactly why they would uncouple.
Okay, and Pradeep also asks, what is the state of the art of frequency range and corresponding power of such spin torque oscillators?
Yes, that's I think that will depend on the type of oscillator. I don't have in my head the kind of maximum for each case. If you want a large power, it's the magnetic tunnel junctions that can give you the large power. But those are and those are typically lower frequency if they're based on vortices. My thinking is that microwatts per root hertz have been generated, and it's about that level. But that would be an interesting literature study actually to do, basically to look at the different types of oscillators, and it probably is in the literature. In fact, that a comparison of the power of different types of oscillators.
Okay. So I think I don't see any more questions. So if there's any, please say it now. So I guess we have a couple more minutes. So I might like to ask you, Andy, because I haven't seen, I mean, not talking about your talk, in general, many work on Skyrmion oscillators, right? So Skyrmions is like a hot topic field. And
yes.
apparently they have good properties that might prevent dissipation. Maybe I'm not so. My question is like, what will one gain in getting a Skyrmion oscillator somehow, if that's possible?
Yes, what would one gain with a Skyrmion oscillator? Well, I think again, I think if you could gain maybe in the fact that it's a collective object, so that it has that you're exciting some kind of modes of that kind of a Skyrmion. So I think it could have advantages like the vortex oscillator in that you have some magnetic volume. I think so that's one aspect. I guess the other aspect is it may be interesting as an intermediate state. I've seen in a switching state, it could be an interesting intermediate state in switching. And maybe the other thing you could do is you want to be able to generate Skyrmions. People want, Skyrmions to be able to do some kind of operations. And I think there it could be interesting that the nanocontact type structure could be a source of Skyrmions. I like that idea actually also, because you want to be able to, if you were to use it for some kind of reservoir. I mean, you maybe need you would want, people have shown you could use a Skyrmion kind of reservoir as a decorrelator. You need a source of Skyrmions. So that could be another interesting aspect of Skyrmions in an oscillating situation.
Okay, thank you. Okay, great. So then, well, I clap for everyone.
Yeah, thank you so much for inviting me. Yeah, thanks. Great to see you and be part of this. Thank you.